Hello, welcome back to our fourth week of the Jerusalem Science Contest. I'd like to begin, we're going to be talking about chapters 9, which is Venus, and chapter 10, which is Mars. And so we'll begin with Venus on chapter 9. Venus is, the angular aspect of Venus from the Earth is 47 degrees maximum from the Sun, so it's never going to be more than 47 degrees away from the Sun. And it's visible at right before sunrise and sunset, usually for about 3 hours before sunrise and sunset. Outside of the sun and the moon, it's the brightest thing that we see in the sky. When it's closest to us, at inferior conjunction, it's at about 0.28 astronomical units. And the sunlit side is away from us at that time, so we can't really see it. The radius of Venus is 0.95 of that of the Earth, so it's nearly the same size as the Earth. Its density being a little bit lower than the average Earth density, which is 5,500 kilograms per cubic meter, and that of Venus is 5,200. Its actual mass is only 0.82 times that of the Earth. But it was for a long time considered to be a sister planet, and it is the one planet that is closest in size to the Earth. Now, it's got a very, very slow rotation rate, and unlike the other objects in the solar system, which are all rotating in the same direction that they're moving around the Sun, Venus is rotating with a retrograde, in a retrograde way. So it's rotating. If we would look from the Sun down, if we could be in a position where we're looking at the solar system and looking towards the North Pole of the Sun, we'd see everything moving counterclockwise around the Sun, and we'd see Venus moving counterclockwise, but everything would be rotating counterclockwise, with the exception of Venus, which is rotating clockwise, which seems very strange. Now, the explanation for that, or one possible explanation for that, was that Venus was walloped at some point in time with a really huge object. So something very, very big hit the planet Venus, probably stopped its rotation entirely, or actually it slowed it down so much, and then it just started to rotate very, very slowly in the opposite direction, just depending on the angle that this object happened to hit the planet Venus. It might have been something really the size of whatever it was that hit the Earth that actually caused the formation of the Moon, but it was a very long time ago. And we've actually got images of Venus that were taken in the UV from in the ultraviolet region of the spectrum from the Pioneer spacecraft in 1979, and we also have later better images from Magellan. And from this, we've actually been able to map, even before something was landed on Venus, we had some idea of what the surface looked like. Also, we have radio images from the Arecibo radio telescope. Back in the 1930s, people used to think that Venus might be inhabitable, and it was thought that it would be a kind of a warm, lush place that would have had a lot of vegetation growing from it. But in 1956, there were some experiments that were done, radio astronomy experiments, that indicated a black body spectrum emanating from Venus that suggested a surface temperature of at least 730 Kelvin. So obviously that would be much, much too hot to support any form of life. Now, what we do know about the surface of Venus is it's relatively smooth. It's got rolling plains. About 65% of the planet's surface are rolling plains. There's about 27% lowlands, which makes up 92% of the planet's surface, and then the other 8% is what we would call continents. You compare that with the Earth, where 25% of the Earth's surface is covered with continents. But on Venus, there's one very, very large continent known as Ishtar Terra, and then there's another Aphrodite Terra as the other continent. So there's also another surface feature that bears mentioning is a great crater known as Cleopatra, and Cleopatra is approximately 100 kilometers across. So we're looking at something that's over 60 miles across, a really huge crater. There's no tectonic activity on Venus, but there is volcanic activity, and this consists, whether these volcanoes are still active or not is not known, but there certainly was at one point in time considerable volcanic activity. What we see are what are known as shield volcanoes, and I think I might have talked about these previously, but shield volcanoes are a kind of it's a volcano that actually forms with a crater at the summit. This is where lava that was coming from the volcano actually withdrew, and it left as it withdrew. It kind of sunk back into the planet and left a crater behind that. So we've got these. That's one feature that we see on the surface of Venus. There's also some uncollapsed structures that are called lava domes, and this is just where the lava was bubbling out and formed it solidified before it actually could collapse. And these things actually, at least from space, they kind of look like pancakes, and these are about 25 kilometers in diameter. There's also a lot of impact craters, but none of the smaller impact craters that you might see, for instance, on the Moon, because of the fact that Venus has a very, very heavy atmosphere, and anything that would enter into Venus's atmosphere that's of a small size would actually burn up before it hit the ground. So the impact craters that we see are fairly large. The first actual photograph of the surface that was actually taken from the surface was from the Venera 9 lander that was sent by the Soviet Union, and from that we learned that at least from the actual color of what we saw, that everything appears to be sort of a peach color, and that's because of the way that the light is actually coming through this very, very dense cloud cover. So it's not thought that there were peach-colored rocks or peach-colored soil, but it was just the way that probably everything is not that color, but it's just the way the light was coming in. The atmosphere is very, very thick, very heavy on Venus. On Earth, 90% of our atmosphere lies from the ground up to an altitude of about 10 kilometers. And on Venus, it goes from the ground to 50 kilometers. So that's the 90% level of the atmosphere. So where our troposphere is, from the ground up to the clouds is maybe, I don't know, 10 or 20 kilometers. On Venus, it's actually 100 kilometers. So it's there's a much heavier, much greater layer of atmosphere. From 50 to 70 kilometers, there's a reflective cloud layer, and that cloud layer consists largely of unlike on Earth, where the cloud layer would have a lot of water vapor in it, this has droplets of sulfuric acid. Below that, to 30 kilometers, is a layer of sulfuric acid haze. Below that is actually a clear. The atmosphere is relatively clear. Above the clouds, there's a jet stream that's very, very strong, about 300 to 400 kilometers per hour. And at the South Pole, there's a polar vortex of swirling winds, which is not all that unusual. We see that in other places. Even the Earth has that to a certain extent. Now, the actual atmosphere, if we measure it, turns out to be 96.5% carbon dioxide and 3.5% nitrogen. There's traces of water vapor, carbon monoxide, and sulfur dioxide and argon, but there's apparently no oxygen present in the atmosphere of the planet. And you kind of would expect that again because of the fact that the planet's surface is so very, very hot, and if there were any gases in the primordial atmosphere of Venus, these other gases, they would have actually evaporated. They would have gone out into space. So even the gases that we're seeing are heavier gases, things with a higher molecular weight, like carbon dioxide, which of course is going to be is not going to move as rapidly. Those molecules won't move as rapidly, for instance, as oxygen or nitrogen. There is, as I said, there is a little oxygen. There's about not oxygen, nitrogen, about 3.5%, but that's still very, very small when you look at our atmosphere, which is nearly 80% nitrogen. Nevertheless, it's believed that at one point in time, the atmospheres of both planets were pretty similar. Both the Earth and Venus had similar atmospheres. So if we want to try to understand why it is that Venus is so very, very hot, we have to look at a phenomenon that we see on the Earth, which is the greenhouse effect. And it's believed that on Venus, you had the greenhouse effect in very, very high gear, what is sometimes referred to as a runaway greenhouse effect. So if it weren't for the fact that that on the Earth we don't have this runaway greenhouse effect, it's calculated that the Earth would actually have an atmosphere that was 95% carbon dioxide and 2% nitrogen, with a pressure of 70 atmospheres. Now the pressure on Venus is 90 atmospheres, so it's kind of a comparable thing. You know, we'd actually have a much more dense layer of gas around us. In fact, we don't have that situation. If all the carbon dioxide in the rocks present on the Earth, that is carbonates, when they're heated up, they give off carbon dioxide. If all of that carbon dioxide and all of the dissolved carbon dioxide in the ocean were emitted to the atmosphere, the situation that I previously described, this 90% carbon dioxide, 2% nitrogen atmosphere, is what we would actually have. So that's relatively close to what you see on Venus. So we have to assume that on Venus, that's exactly what happened. If it had oceans, its water vapor all evaporated, and all the oxygen bled off into space. And what you were left behind with was a large amount of carbon dioxide and a very, very small amount of nitrogen. So, being closer to the sun, it's 30% closer than Venus is 30% closer on average than we are. It's a lot hotter, and so water vapor would never have condensed into oceans probably. And therefore, the water and the carbon dioxide, whatever was there, remained in the atmosphere. And an explanation of how the greenhouse effect works, I just wanted to show you briefly here. So this is what we have on the Earth. We've got the sun, and the sun is beating down on the surface of the Earth, making the sun small because we're thinking of the distant sun. Beating down on the surface of the Earth, and we have our atmosphere, troposphere, stratosphere, etc. We have in the atmosphere there are a lot of various gases. So we've got oxygen and we've got nitrogen. These are normal constituents of the atmosphere. There's a small amount, something like 0.03%, but I should say, and growing, of carbon dioxide in the atmosphere. So a very tiny amount, 0.03% of carbon dioxide, and about 19% of oxygen. There's 1% of argon in our atmosphere. Now, these gases, oxygen, nitrogen, argon, are not what we refer to as greenhouse gases. Carbon dioxide, however, is one, and it has to do with this, that when the sunlight is coming in, and it's all different wavelengths of light that are actually entering the Earth's atmosphere. But a lot of this, maybe in the far UV, is actually being blocked out. The most harmful frequencies of ultraviolet light are being blocked out. A lot of infrared radiation is coming in, and a certain amount of a lot of visible radiation is coming in as well. Well, what happens is when this
particularly if we're looking at in the visible region of the spectrum, what happens is the visible region, in the visible region, the light, the visible light is going to come in and it's going to strike the ground. So when it comes in and it hits the ground, it's actually going to, some part of it will be absorbed, some part of it will be reflected. But even the material that is reflected, energy is lost, and so we get a lower energy wave that is actually emanating back or is reflecting back off of the surface of the planet. So let's say, for instance, visible light comes in the red region. When it goes out, it's going to come out at a higher, at a lower frequency and a higher wavelength, which means it will be in the infrared. So it's going to come out in the IR, comes into the red or anything in the visible, and it's going to be actually shifted back out into the IR, which of course, in the infrared, that's where we're going to get heat in. So normally this isn't a problem. What happens is this radiation, along with any other radiation, is just going to be reflected out into space. The heat is going to will actually be reflected out into space, the infrared part of it, and that doesn't really affect us very much. Our planet would be a lot colder if we didn't have a small amount of carbon dioxide in it, because what that carbon dioxide does is the carbon dioxide molecule, which looks like this, actually is very active in the infrared region of the spectrum. So it absorbs in the infrared, and we can actually, if we look at this, look at the absorption spectrum, you'll see a big peak that corresponds to the stretching of the carbon-oxygen bond. So this is basically the bond is getting shorter and longer and shorter and longer. That stretching mode gives us a big peak that we can actually measure. And because it's absorbing this energy, what that means is that these molecules are actually heating up a little bit, and some of that actually gets reflected back down to the Earth. Some of it, of course, will leak off into space. Some of it will be reflected down to the Earth, and it's the reason why it does get cooler at night, but we don't lose all of the heat, because we have that little bit of carbon dioxide in there, and that's kind of acting as a blanket. As we get more and more carbon dioxide in there, however, what happens is that effect becomes much more pronounced, and it's not possible for all that heat to radiate off into space. So this is why we're concerned, or we should be concerned. Some people think that so-called global warming or climate change is a figment of scientists' imagination. But the vast majority of the scientific community certainly believes that this, in fact, is what's happening, and it probably is due to gases like carbon dioxide. Water is also, to a lesser extent, water vapor is also a greenhouse gas, but we're more concerned about levels of carbon dioxide. And there are other things that we, man-made things that we put into the atmosphere that also have this kind of an effect. So anyway, this is the greenhouse effect, and on Venus, it's really gotten completely out of control, because you've got this huge cloud, a rather huge atmosphere, a very thick atmosphere, crushing pressure from this atmosphere. 90 Earth atmospheres, so 90 times the pressure. You've got columns of gas pushing down on you at 90 times the force that we're experiencing on Earth. So this is a tremendous. This would be a tremendous pressure. Even if this were an oxygen atmosphere, you couldn't live at that kind of a pressure. That would kill you. So these are the very inhospitable conditions on the planet Venus, and that kind of is an explanation of why that is. One other thing that I might mention in passing is the fact that Venus has no magnetic field. It has apparently an iron core, and so it looks a lot like Earth in that respect. But the difference is that on Earth, you've got this molten iron core and the Earth is rotating at a significant rate of speed. And what's happening is whenever you have this molten metal, this molten iron in motion, it actually generates a magnetic field. Now, in the case of Venus, there's also a rotation, this retrograde rotation, but Venus's rotation is very, very slow.
Well, it's in your book, and I don't remember the number myself offhand. But it's Venus is rotating very, very slowly, and it not only does it have this retrograde rotation, but the rotation is quite slow, so that precludes the formation of a magnetic field. And Venus geologically is very, very young compared to the Earth. So Venus right now is where the Earth was about, I would say, approximately when the Earth was like a billion years old. So about 3.5 billion years ago, it's about where the Earth was about 3.5 billion years ago.